Okay, so let's take a look at section 5.4. Okay, as I said earlier, we're going to split it into 2 days. Okay, half of it today. The second half tomorrow is pretty short, but it's just long enough that I don't think we want to try to squeeze it in with the stuff from today. So a log function is the inverse of an exponential function. Okay, I'm going to show you in a little bit what that means visually. Like if you draw 2 functions that are inverses of each other, they have a certain look to them. They have there's like a symmetry. So let me just show you like something basic. Let's take a look at the squaring function. But I only want to look at the squaring function for values greater than 0. You'll see why in a second. I guess greater than or equal. What's the inverse of squaring? What function cancels out squaring? Yes? Square root. So let me graph both of them so you can see what they look like. That's automatically built in to have x is greater than 0 because square root of a negative would be imaginary. So let's see what that looks like. Ignore that part. There's your square function. And there's your square root function. They're mirror images of each other. What they're a mirror image over is the line y equals x. Okay? They're flipped right over that black line. So if that was like a piece of paper and like that red ink was wet and you folded it right on the black line, it would land right on top of the blue one and make a mark right there. All inverses follow that same idea. They're all mirror images over that black line. Okay, we're not studying square and square rooting. We're studying exponential and log. So I'll graph those in a minute. So the reason why I had to put in that little condition of x greater than or equal to 0 is because in order for a function to have an inverse, like a square function, it has to pass the horizontal line test. Well, if you graph the square function and you don't put any restriction, it looks like this. Horizontal line test says if you can put a horizontal line and it doesn't hit the graph more than once, it has an inverse. Well, the regular x squared function fails the horizontal line test. All right? So that means if I were to try to sketch the inverse of a full parabola, its inverse would not be a function. Okay? It would not be a function. So if I have a graph and I want its inverse to be a function, it has to pass the horizontal line test. If I have a graph and I just want to know if that graph itself is a function, then it has to pass the vertical line test. Okay, so vertical line test has to do with the actual function. The horizontal line test has to do with the inverse. And it tells you if the inverse is a function. Okay. Well, exponential functions already pass the horizontal line test. So we don't have the same problem with like a square and square root, like that example. Exponentials look like this. No matter where you put a horizontal line, well, I didn't want them grouped together. No matter where you put that, it's never going to hit the curve more than once. So because exponential functions pass the horizontal line test, then the inverse of that function, or the inverse of that, is a function. So we don't know what it looks like yet, but it's going to be a function. Okay, so exponential functions pass the horizontal line test. So the inverse of an exponential, whatever it is, will be a function, meaning it passes the vertical line test. I already told you that. So inverse functions are reflections over the line y equals x. And what you're looking at in blue is an exponential. And the calculator has a little trouble drawing the inverse because what happens is it gets so steep down, just like it's so steep up, it can't really draw it. So this should continue basically like that. All right. So this horizontal part in blue, it's not quite horizontal. It's very flat, but it's never horizontal. But it looks horizontal. That's what becomes the vertical part in red. This part that curves up very quickly in blue becomes the part that curves up very slowly in red. Any questions on that? The fact that those are inverses and how they're mirror images. Okay. So that function that I drew is a logarithm. Okay. Logarithms are the inverse of exponential. Just like square is the inverse of square root. You can use those two things to cancel each other out. So that might give you kind of a hint if you had a problem like this. That's an exponential problem because it has a variable in the exponent. To undo an exponential, we need the inverse of it, which is a log. So if you wanted to solve this equation, you would use a logarithm. Okay, the way you pronounce what I have in black is y equals log base a of x. Okay. And just to be clear how that is written, if you had a piece of lined paper, it would be y equals log base a of x. The a is actually like a subscript. Okay, the x is not an exponent. An exponent would be up here, log base a of x squared. Okay, so the x is just right on the line with everything else, and the a is a subscript. Okay, the name for the x, that's called your argument. The argument is just the thing you plug into the log function. Okay, a lot of functions have arguments. In fact, all functions have arguments. It's just the thing you plug in. So like, if I take the square root of 8, we call 8 the radicand, but if you want it to be a little bit more general, you could just say 8 is an argument. It's what you plugged into the function. Okay, and I get an answer. The sine of 15. 15 is the argument. It's the thing I'm taking the sine of. Right? And same with log. Log of 40. 40 is my argument. It's what I took the log of. If the base is 10, okay, if you write a base 10, that log has a special name. That's called a common logarithm. Okay, usually abbreviated common log. It's the log we always assume if they don't tell me a base. So in algebra, we kind of assume certain things, like if you write a variable and there's no number in front of it, we assume it's a 1. Well, if you have a logarithm and you don't put a base, then the base is 10. The common logarithm is one of two bases that the calculator can do directly by pressing a single button. All right, so if I wrote this log base 10 of 30, it's exactly the same as writing this, log 30. Common log, the way the calculator will do it is the way that's on the right. So when I type in log 40 right there, the calculator is assuming I want base 10. If I don't want base 10, well, there is one other button on the calculator that we'll talk about that has a special base. But that's it. There's only 2 buttons on the calculator for logs. So if you want to do a base that's not one of those two buttons, we got to figure something out. Okay, because you can't have a base for every single button. Okay? You can't. That'd be like having a special button on the calculator for every single exponent you could ever have. Like 2.5, 6.4, you can't. You got to use the buttons you have to type in more complicated things. So we'll figure out how to type in bases that are not 10 and not the other base, which I'm going to show you in a second. Okay, the other base is e. So remember yesterday I did a graph and it had a horizontal asymptote and it got very close to this number 2.718. Well, I said we'll talk more about that number tomorrow, and now it's tomorrow. So base e is a special base, and it's called the natural log function. It's the other log that you can do directly on the calculator by just pressing a single button. So common log, base 10, natural log, base e. And if you're doing something with log base e, you will never see something like that written. They don't write that. Okay. There's an abbreviation for that we use. And the abbreviation is lowercase l, lowercase m. Natural log. Why did they do NL instead of LN? I don't know. But they used LN. Okay, so LN is a short way of writing log base e. So when you write LN, the e is still there as the base, it's just hidden. Okay, it's hidden in that abbreviation LN. So in a problem, if I ask you to find the log base e of x, I'd have to tell you what x is. Or I ask you to find the natural log of x, ln x. It's the same thing. Okay, on the calculator, the way you type it in, it's going to look like what's on the right. ln x. And the button, just to show you where that one is, it's right below the log button. So if you press ln, type in something, natural log of 85 is 4.44. Any question on that? What was E again? Roughly what number? About 2.718. Watch this. 2.71828. I just know a couple extra ones. If I raise that to the 4.44265 whatever it is, I get 84.999. Basically, I get 85. 85 is what I had right there. So this number, 4.44265, is an exponent. Anytime you hit the log button and you hit enter, the answer that you get on the screen is an exponent. An exponent to what? Well, it depends on the problem. But logarithms are exponents. Okay, let's make sure you remember that. Logarithms are exponents. That's why when you have a variable in the exponent, you use a log, because the logarithms will find what exponent should equal. All right, let's go back to our picture for a second. And actually, I think I just did it on here. Okay, looking at the graph in red, that's a log function. What does it look like the domain of that graph is? If we look at how far it goes left to right, it looks like it's going one direction forever, but it kind of looks like it almost hits a wall and it stops at one point. Yeah?
It looks like it almost reaches 0.
It almost reaches 0, yep. Yep. The graph in blue has a horizontal asymptote at 0. The graph in red has a vertical asymptote at 0. That's what always happens with inverses. Everything that was horizontal becomes vertical. Everything vertical becomes horizontal. It all switches. So it goes almost to 0, but up to infinity. And how about the range? How far down does it go, and how far up does it go in red? Yeah. Negative infinity to infinity. It goes down very sharply. It goes up extremely slowly. In fact, I'll graph the log function. We'll go to the table. And then let's just take a look at how slowly it goes up. It's a log function. So you can't do 0. That's why I put a parenthesis on it. You cannot take the log of a number that's 0 or lower. Logs have to be positive numbers. Only take the log of a positive number. So if I take the log of 10, and this is just common log. I'm just doing an example of something specific. The y value is 1. If I go to 500, I went up 490 units on the x. I only went up like 1.7 units on the y. Didn't go up very much. If I go all the way to 9,000, going up another 4,500 units on the x, it only brought me up 1.3 units on the y. So it's very, very little for how much you have to go on the x-axis compared to how much you gain on the y-axis. Okay. It'll always keep going up, but it goes up slower and slower and slower. Okay. It's the slowest growing function that we really have in math. All right. So one thing we want to be able to do is convert between something that's written in log form and something that's in exponential form. Just to show you an example of each. That's a problem in log form. That's a problem in exponential form. Okay. Exponential form usually has exponents. There's no log in there. That doesn't have any exponents, and you see the word log. Okay. So it's just a matter of moving things around. Okay, for the formulas that I'm going to give you, we're going to assume that a is a positive number that's not 1. Okay, any positive number you want, except 1. Right, so when you write something in log form, there's 3 things. There's the base, there's the argument, and then there's the letter that was on the other side. So we have a. We have the a, the x, and the y. When we write it in exponential form, which is what's on the right-hand side, the first thing you want to do is you get rid of the word log. That goes away. And then I look at my log and I say, okay, what was the base on my log? What was the thing that was written a little lower? It was a. When I write it as an exponential, the a is going to stay as my base. It's just not going to be the base on a log anymore. It's going to be the base for something that gets an exponent. So whatever the base on the log was, that's going to be the base on your exponential. How do you figure out what the exponent should be? Okay. Well, that's the phrase I told you earlier. Logarithms equal exponents. Logarithms are always used to find exponents. So whatever a logarithm equals, like what I have the green box around, that's an exponent. That's why in exponential form, the y becomes the exponent. So you've got your base. Logarithm always equals exponent. If you know where 2 of the things go, there's only 1 spot left for the third one. And that's x, and that goes by itself on the other side. Okay, so changing log to exponential, the argument ends up alone. Just think of it like if you argue with someone, you're going to end up alone. You're going to get annoyed, you're going to walk away. Okay. So the argument, it ends up alone. Okay. Or however you want to remember it. Okay. So let's just practice changing between the 2 forms. Okay. Let's start with this one. I'm not always going to put colored boxes around them. I'm just trying to do that for the first one. To highlight the 3 things. Okay, let's start with my base. Jared, what's my base there? 3. So when I rewrite it as an exponential, 3 is going to be the base. Now I need to figure out the exponent. So my choices are the x and the y. What's going to be the exponent on the 3? Okay. Yep. Which one? You said x? No, not x. Remember, logarithms always equal what kind of number? Exponent. Logarithms equal exponents, always. So whatever y is, it's equal to a log, that means it's an exponent. Now, what do we call 3 the base? What do we call the x again? Yeah.
The argument.
It's the argument. Remember, argument, you're going to end up by yourself. Okay? Argument, you end up alone. So the x goes by itself on the other side, and that's all you can do. If you knew, like, what y was, let's say y was 2, then you could actually do it out, 3 to the second power, and get an answer. But unless we know something else, we're done. Any questions on that one? All right, let's try this one. Y equals log base 5 of x. That is how you pronounce it. Don't say like log 5x or something like that. Log base 5 of x. Okay. So just by pronouncing it, you kind of already say what your base is. So Gabe, what's the base here? 5. So I end up with 5 as my base. How about Jacob, what's my exponent?
5.
We already used that. So the choices are now y and x.
Bx. Y.
One of those. X or y. Anyone? Yeah?
Why?
Y. How come?
Because it's the exponent, I guess.
Right. Logarithm always equals the exponent. Log equals exponent. Just like put that in your head. Logarithm always equals the exponent, and the only thing left is the argument. Or if you argue, you end up by yourself on one side. So there's another one. Again, nothing you can do further with that because you don't know a couple things. Questions on that one? Okay, well, let's try the other way. So now we have something that's an exponential, and we're going to change it to logarithmic. Well, if we're going to change it to logarithmic, what's the very first thing we need to write down? Before you even look at numbers or letters. Yeah?
Log.
Yeah, we put the word log. Log. All right. Now, I usually start with the base. Gabe, if I look at my base in the exponential problem, what is it? 1.2. So that's going to be the base of my log. All right. Now, logarithms always equal what kind of number? Emily?
Exponent.
Exponent. So now my exponent is 3. Now there's only one thing left. I need the argument. Remember, arguments always end up alone. So that's your argument right there. And that's it. Unless you knew what M was, I mean, you can't really do anything more with that. All right, let's try this one. E to the B equals 9. All right, so we'll start with the word log. And Renee, what's going to be my base? E. If you look at the exponential, the base is always the thing that's a little lower than the number that's above and to the right of it. So E is my base. We'll come back to that in a second. So E is my base. Evangeline, logarithm always equals what kind of number? The exponent, so B. And the only thing left is 9. Now, I'll just put it below it. I can simplify that because there's something there we normally don't write. We have an abbreviation for it. Does anyone see what I can abbreviate? Chris?
Your log base e to ln.
Yeah. And if I wanted, that's something I could actually type in on the calculator and get an answer. The ln of 9, it's about 2.2. Okay. I don't really care to round it, but that's what it would be. Right, so what that means is if you took e and raised it to the 2.2 power, you would get 9. Well, roughly, or 8.9. So we just solved for an exponent. That's kind of more of the same. All right, I want to show that what's on the left and what's on the right are equivalent. Well, I only know how to do one thing with logs so far, and that's change between the two forms. Nathan, what form is that one in?
It's just like the log form.
That's log form. So let's change it to exponential and see what happens. So Blake, could you change that whole thing to exponential?
2 to the third.
So 2 is my base. Logarithm always equals the exponent. And what would go on the other side? 8. So the 2 went the base, 3 is the exponent, 8. And the question is 2 cubed equal to 8? Yeah. So we showed that they're the same. So that might give you a little bit more idea about how logs work. When you see something like this, it's basically saying 2 to what power would give you 8. Right? So if I wrote something like that, that's asking if you wanted to simplify that in your head, which you can do. It's saying 5 to what power is 25? So the answer there would be 2. When you can't do it in your head is if I did something like this. Now that's saying 6 to what power is 25? Well, we have to, it's less than 2. So we'd have to use a calculator to figure it out. But we don't know how to use a calculator yet because look at the base. It's base 6. The only bases the calculator can do are what and what?
10 and E.
10 and E. 6 isn't a 10, 6 isn't an E. So there is a way to type that in, but not yet. Okay. Let's look at this one. Log base 5. It's almost actually the same question I just did, except instead of 25 as the argument, it's 1/25. So think of this in exponential form. Base, exponent, number on the other side. What kind of value does x have to be? You don't have to be specific, but I just want to know because I'm taking a number raised to a power and I'm getting a fraction. Yeah?
It has to be negative.
It has to be negative. And if you're stuck, just see if you can solve this problem. It's not the same answer, but the number's the same. You just put a negative in front of it. So 5 to the second power is 25. 5 to the negative second power is 1/25. Any questions on that? All right. Let's try this one. Joe, what form is that equation in?
Log.
Yep, that's log. The only thing we know how to do is try changing it to exponential and see what happens. Could you change that to exponential for me?
So that would be 1.5. No. 5 to the 1.5. Yeah.
Equals x. Yeah, so 5 to the 1.5 equals x. Now just type it in. 5 to the 1.5. So it's about 11.18 if you wanted it this small. question on that one? All right, that's more of the same. That's, well, actually it's a little different because there the variable is in the argument. Here the variable is in the base. So let's do it. It's in log form, so let's change it to exponential. Yeah.
Maybe x to the second.
Yeah. X squared equals 3, and now you can't solve that with adding or subtracting. We got to cancel out the square function. And we do that by doing what? Take the square root. So x equals the square root of 3. Now, when you take a square root, how many answers are there? 2. Remember what I said about logs. You have to have positive numbers in those spots. You can't take the log of 0, and the base can't be 0. And you can't take the log of negatives. All right. So neither the base or the argument, neither one of them can never be 0 or smaller. They have to both be positive numbers. All right, so we're going to look at a couple special properties of logs. So the properties, this is like the last part of the class. These are just special patterns that if they come up, there's no real work to do. It's just a pattern to recognize, and you'll automatically know the answer. If you have something that looks like that, a to the log base a of x, that's exponential. It's just that there's a log in the exponent. Well, what ends up happening is if the base on the log and the base on your exponent are the same, it's almost like these just cancel each other out. And all you're left with is the argument to the log function, and that's the answer. So like if you had 2 to the log base 2 of x, well, that's an example where all of that would cancel out. And the answer is whatever number is right there. If it's an x, the answer is x. If it's a 4, the answer would be 4. But everything cancels out except that. Okay. So it's just a special pattern. Let's look at this one. Okay. That's an equation that's in log form. Here's your base. Here's your argument. Here's the thing that's on the other side. If you have an equation in log form and it has a base, and then the argument has the same base, they cancel out. It's like all this just disappears. And the only thing left is the exponent. Okay, let's look at why that one's true. Okay? To look at why it's true, I'm going to change it from log form to exponential. And the reason why it's true is a property you all learned in geometry. So what's my base in that expression? Yeah? A. That's my base right there. So A. What's my exponent? Yeah? X. Logarithm always equals the exponent. That's my exponent. Now the only thing I haven't used is the argument. That's right there. A to the x. This is the reflexive property. That's all that it is. It's saying that something equals itself. I think most people would recognize that property like that. When you write it as a log, it looks a little different, but it's the same property. It's the reflexive property. All right, let's look at this one. This says that log base a of a is 1. So like log base 5 of 5. 1. Okay, let's see why this one's true. What's my base here? Yep. So this is my base. A. What's my exponent? Am I? 1. That was right there. And what goes on the other side by itself? The only thing I haven't used, the argument. All that property 3 is saying is that if you raise anything to the first power, it doesn't change. You get the same thing back. Okay. Another property that you would have learned in Algebra 1. Anything to the first power is itself. just written the way you see it in Algebra 1, written as a logarithm. Okay, and let's look at this one. Log base a of 1 equals 0. So if you take the log of 1, it doesn't matter what the base is. The answer is always 0. Kathleen, what's my base there? There's my base. A. Rachel, what's my exponent?
0.
0. So that's that part. The only thing I haven't used yet is the 1. So the last property is saying if you raise anything to the 0 power, the answer is 1. Okay, another basic thing from Algebra 1. But just written as a log rule. Okay, and I didn't show you why the first one is true, but I could do the same reasoning. It ends up being another reflexive property again, like number 2. All right, so let's see if we can simplify that using one of our properties. So I've numbered the properties 1 through 4. That's not really important, just to reference them. Which log property does that one look similar to? 1, 2, 3, or 4? Bethany? 1, yeah. Looks very similar to number 1. So if we were going to solve it, what would the answer be? What does x come out to? Pi, 3.14. That's the answer. Okay, again, there's no arithmetic. There's no real process to go through. It's just a special pattern. All right, let's look at this one. Log base 0.2 of 0.2 to the negative 4. So if you had something like that, the directions might say simplify. Just tell me what it equals. What log property is that one similar to? It's very similar to 2. And if you follow that property, what do you get? Yeah. The answer there is negative 4. Now, if you change the 0.2 to 0.3, just change one of them, don't change the other one, then you can't use this special property. How about this one? The ln of e to the kt. This one's a little hidden, but it is one of those properties. Anyone think they see what property that is? Did anyone see what property it is? Yeah? It is the second one. Remember, how can we write ln? Instead of writing it the short way, let's write it the long way. Yeah? Log base e. What I just wrote can take the place of what I just underlined. Now write down everything else. E to the kt. Now it's more obvious that it's property 2. So what would the answer be?
X equals K2.
Yeah, it's just kt, whatever k times t is. Okay, I didn't give an example of properties 3 or 4, but any questions on those? Just look for that pattern. All right, so last thing we're going to look at is kind of the third thing. So first thing was just kind of the basics about logs, then we looked at special properties. Now we're going to look at how we can take logs and either combine them together or separate them apart. Okay, so we'll do a few combining and a few separating, and that's it. So this is a rule that you can use with logs. If you have the log of a product, it could be 2 things, 3 things, 4 things. The more factors you have in your product, the more terms you'll have when you split it. If you just have 2 terms, or 2 factors, it splits into 2 terms. A product splits as a sum. Notice the base stays the same. Whatever the base was when you started, it's exactly the same when you split it. So that's an example using numbers. If I had log base a of 4 times 5, I could write that as log base a4 plus log base a5. Now, I'll show you how that works out, and I'll pretend that I'm going to use base 10. So I'm going to do this with a specific example. It'll be the common log. So let's do log of 4 times 5, which is just 20. You get that? Here's the log of 4 plus the log of 5. Comes out exactly the same. In fact, any two numbers that multiply to give me 20 would work. I could do log of a half plus log of 40, because 40 times a half is 20. So any two numbers that multiply together to give you 20, you could split it as a sum, where each argument is one of the original factors. All right. We also have the same property for division. But division doesn't split as a sum. What do you think would happen with division? Any guess? I mean, if you could hope for anything nice to happen in math, what would you hope for? Yeah.
Subtraction.
Besides having it just all go away. Yeah.
Subtraction.
Subtraction. So if you have division, like m divided by n, you can write that as a difference of two logs. Whatever the base on the original was, that's the base when you split it. The first argument is your numerator. The second argument is your denominator. It has to be in that order because subtraction is not commutative. So I'm not going to go through this one, but you could try typing that in, and it would work. Now remember, you can use these properties with any base. Base 10, base 5, doesn't matter what the problem is. It works on any base, even base e. So if you had ln of 4/5, that would be the ln of 4 minus the ln of 5. So it works there too. Okay, let's look at our third property, which is really kind of like the first property. Except instead of having different factors, I'm going to repeat the same factor inside. So let's do log base a of y times y times y. So we know that when you have a product, it splits apart into a sum or difference. Yeah, sum. This is going to have 3 terms because I have 3 factors. What's going to be the base on each of my logs when I split it? A doesn't change. Whatever the base was in the beginning, that's what it is when you split it. What's my first argument? Oh, right? Y. My second argument? It's also y. And my third argument? Y. So I have log base AY plus log base AY plus log base AY. How many of those do I have? 3. Log base A, Y. And if you look at this, and then think of it this way, what's a shorter way of writing y times y times y? Y to the third. Look at what you started with, and look at what you ended up with. What ended up happening? Exactly. The exponent moved in front. That's the third rule. If you have an exponent on an argument, you are allowed to take and just put it in front. This is the reason why. So we're not going to go through the steps in the middle ever again. So log base A of m to the r, you can take the r and put it in front. I already gave you an example, but if you want another one with all numbers, there it is. Log base 10 of 3 to the 5th equals 5 times log base 10 of 3. Or you could pronounce it 5 times the common log of 3. All right, so the last thing before we look at a few examples to finish up is if you have certain exponents, there's a connection between exponents and roots. Does anyone remember for the square root what power you can write a square root as if you don't want to put the symbol? Yep. 1/2. So we already went over that. I'm just reminding you. Because square roots hide exponents. So we're going to have something with rule 3. Right? Kind of like this. If I asked you to simplify that, there's an exponent there and it's hidden. It's really this. It's really x to the 1/2, and we are allowed to put that 1/2 in front. So something like that's going to happen. Right? Not with cube roots or anything else, but with a square root. So just remember, square root is hiding an exponent, which can go in front. All right. So we'll do a few problems where we separate, and then we'll do a couple where we combine. It says separate into multiple logarithms, express powers as factors. What that means is do not leave exponents. Move them in front so they are multiplied. That's a factor. Move it in front. Okay, so let's start with this one. Log base 4 of 3x. When I split it, would it be a sum or a difference? Sum, yep. It's going to be a sum. What's going to be the base on each log? Yeah, 4. Base doesn't change. What's going to be the argument to my first log? Yeah, 3. It's my first factor. And what's going to be the argument to my second log? X. That's it. It's a relatively easy one, but if you get that, it doesn't really get too much out of it. Okay, let's try one like this. Log base 2 of 5 times r cubed. So Madison, when we split that up, is it going to split as a sum or difference?
A sum.
Yeah, it's going to be a sum. It's still something times something. Even though the second something is a little more complicated, it's still something times something. So log. Tori, my base on each log? 2. And how about Joe, what's my first argument going to be? 5. Now my second argument would be r cubed. But if I want, I can do something at the same step. I got to do this eventually. Either do it now or later. So what do I have to do with the cube? Yep. Put a 3 in front. So if you want to do it all in one step, there you go. Log base 2 of 5, 3 log base 2r. All right, let's try this one. Kathleen, sum or difference? Difference, I agree. Difference, log. Nathan, base on each log?
Base 9.
9. Kaylee, my first argument?
X.
Yep. And how about Jarek, my second argument?
2.
2. Okay, so that one's a difference. Anyone think they could tell me the whole answer to that one? You don't have to write log base e. You can leave the ln because that's an abbreviation. So your answer is going to have ln's in this one. Yeah?
So it would be 3 ln y minus ln e.
Yep. That's it. 3 ln y minus ln e. Okay, let's skip to the last one for these, and then we'll do a couple combining. Let's look at this one. Okay, so it looks more complicated, but really you're just going to do it one step at a time. Whenever you split logs, I see 2 things. I see a product, but I also see a quotient. Always handle the quotient first. That's what's in the top. that's what's in the bottom. When I have a quotient, how does it split? Sum or difference? Difference. So it's log base A, put what's in the top, minus log base A, put what's in the bottom. So what we're doing is we're kind of breaking it down into littler problems. X cubed times x plus 1 to the 4th. I put a big set of parentheses around that to make it clear that that's all part of the log. Okay. The calculator would probably show it with like a bigger one and a littler one, kind of like that. Now, this first one, we have to be a little careful. There's a square root in it. And the directions said to write powers as factors. Well, you might look at that and say, I don't see a power there. But a square root is hiding what power? A half. So what I could really do is put x plus 1, again, parentheses to make it clear that all of that is going into the log. And I could put a 1/2. But eventually, where's that 1/2 going to have to go? They want it in front. That's what they said. So the first part's done. There's nothing else you can do with that. Second part. I have the log of a product. How does a product split? Sum or difference? Sum. So I'm going to have log base A plus another log base A. Now, my first argument would be x cubed. But what can I do with the 3? Yeah? Put it in front. You don't have to do this all in one step like that. You can do it in 5 or 6 steps, but it just saves a little writing. Now, my next argument would be x plus 1 to the 4th. What can I do with the 4? Yeah. Put it in front. Keep the parentheses around x plus 1, because if you do that, I would look at that and say you're taking the log of x, and then you're going to add 1 later. That's not what you want. You want the log of that whole thing. Okay? And that's it. That's splitting it apart. Okay, we'll do 1 or 2 combining. I think combining is easier because at each step it gets shorter and shorter, versus splitting it, it gets bigger and bigger. Okay. Yeah?
Why would we, in the first part, like the first log thing, why wouldn't we do anything about the x cubed or squared?
Because we don't have a rule if there's a sum inside the argument. The only rule we have is when there's a product inside the argument or division. That's the only time you can do anything with it. Okay. All right, let's try this one. Now it says to combine it into 1, make factors as powers. So now you do everything in reverse. It's the same steps. What would happen to this 4 if we're going to reverse everything we did, pretending like that would have been a final answer we just got? Yep. Put it back as an exponent. Log base A 7 plus log base A of 3 to the 4th. At this point, we might as well do 3 to the 4th power and just write what that is. Okay, and I'll do that in the next step. This, when we combine it, we're going to have a single log. Rachel, what's going to be the base on my log? A. And I had addition. How does addition recombine? Multiplication or division? Okay. Multiplication. First argument, second argument. 3 to the 4th is 81. Now just do 7 times 81. Yeah, 567. So that's an example of recombining. Let's just, does anyone want to see the last? Do you feel like we need the last one? Okay, we can do more recombining if we need to. There's some in the homework. We can go over those tomorrow. So homework, page 292, 1 through 7, 13 to 17, 21 to 27, and 29 to 33. So today, notice we didn't focus on anything with graphs. Tomorrow, we'll do a little bit with graphing on logs, and maybe solving some other kinds of equations.